Okay, let's be honest. No one really wants to talk about this because it's sort of depressing, but I'm just going to go ahead with it. So there is some math here. We can try to model exponential growth. Of course, I'm talking about the coronavirus 19. So let's just get into it. Maybe this will get our minds off of it. I haven't fully worked through this, so just hang out here with me for a little bit. Okay, let's see. So I've made a picture. Let's see. No, that's not the one. That's not the one. That's it. No, that's not it. It's this one. No, this one. There we go. Okay, so this is how we model exponential growth. So suppose I have some population N. Okay, and these could be the number of people infected. It could be radioactive, decay. Really, it could be. It's the same thing. It could be any number of things that are modeled exponentially. So N is my population of infected people. Okay, with coronavirus. It turns out the more people that are infected, the more people get infected, right? Because everyone is, interacting with other people. The more people that have it, if there's only one person, they're only going to infect, 2, 3, 4. That's a bad situation, but they're only going to infect maybe 4 people. If there's 5,000 people that have it, those 5,000 people are in contact with even more people, so the rate that people get infected is greater. So that's this is our basic rate equation for exponential. The change in N with respect to time is equal to some constant times the number of people that have it. And I'm just going to start off with a constant of 0.2. Okay, so the first thing we want to do is, how do you model this? Don't worry about this other stuff down here. So if I take delta N as N2 minus N1, where N2 is the number of people infected at some time, and N1 is the time at the beginning of that, then I can solve for this equation. All I did was say this is N2 minus N1 and solve for N2, and I get this. Okay, so this is how we're going to model the exponential growth. And I'm going to show you how to do this in Python. So let's switch over here to Python. Okay, so here's Python, and my window's all messed up. Okay, so let's go ahead and make a graph. This is nothing important. It's just, I'm just going to type it in here. So we have the X title is days. I'm just making that up. And then the Y title is number infected. Okay, now I need to plot something. So F1 equals G curve, color equals color dot blue. I always pick blue. I have no idea why. So now let's go A equals 0.2 and N equals 1. Okay, and now I need T equals 0, dt equals 0.1. Okay, so that's my times up. How often do I recalculate this stuff? And we can change that. So let's just say while t is less than 15 days. Okay, so the first thing I can do is calculate the new number of people infected. So that's going to look like this. N equals N plus A times N times dt. And now this should look weird, right? Because this looks like, oh, the ends cancel. You get 1 equals 1 plus A dt. But this is not an equation. This is the assigned variable. This says take the old value of N, multiply it by dt, multiply by A, and then add it to N, and then make that equal to N. So this is really N1, and that's N2. I know it looks weird. Now I need to update time. T equals T plus dt. Now I need to graph F1 dot plot Tn. And I feel like I'm missing something here, but let's just run with it. Oh, okay, that worked. Okay, and this is not quite. Let's just make this width equals 450. I'm just playing around with stuff. That's a little too small. 500. No, that's too big. Oh, I did it wrong. 500. See, we can still have fun. There we go. It fits. Okay, so there's our exponential growth curve. You can change this. Let's just do something fun. Let's say F2 equals G curve, color equals color dot red. So now I have another one, and I'll call this N2 equals 1. A2 equals 0.01918, let's say. So it has a lower infection rate. Same time, but now I need to calculate this to a comparison. So N2 equals N2 plus A2 times N times dt. And then I need to plot that one, F2.plot T N2. And so you'll see that with a slightly different rate. So this is that social distancing stuff, right? If we can reduce this, we can make a difference in the end. And this is just over a short amount of time. What if I make this 35 days, 45 days? That's fine. You see here, yes, that looks huge, but look, this is 7.6 thousand, and this is 7,000. So this is 500 different people, okay, infected. Okay, but you can play around with that, and that's just a small change. But now, what about actual data? Does the actual growth, can we model this actual growth? Let me say this. I can put this in the link. So let's see. Exponential growth 1 video. I'll save that. I'll post a link to this in the comments down below. Okay, so we did that. So, now let's do this. So what if we write this as a differential function? So now I take the limit as delta t goes to 0. Then I get this. I get a derivative of n with respect to t is equal to a times n. Now this is a differential equation. It's a little bit more difficult to solve. So what I can do is multiply both sides by dt, divide both sides by n, and then I can do some stuff. I can integrate both sides. But the best way to solve differential equations is to guess. If I guess this function right here for the rate, if I take the derivative of this with respect to time, I get the same thing back times an a. And so that's why this function satisfies that differential equation, and this function does indeed work. So let's plot this and see if we get the same thing. Okay, let's do that. So let's go back over to our graph right here. Let's use F2 for this, the actual data now. Yeah, I was trying to think if I should make it a different thing, but let's just do this. So F2, let's leave that there. We need an N0. N0 equals 1. That's the starting one. But other than that, I'm just going to calculate N2. Let's comment that out. N2 equals N0 times the exponential of a times t. And let's see if we plot that. It should work. Yeah, so they're right on top of each other now. And in fact, if I make this dt too big, they don't agree. Because the numerical calculation's only doing it so often. The smaller this time step is, this is the theoretical correct solution. The red curve is. Yeah. So if I make this super small, 0, 1, they'll be right on top of each other. Okay, and you can't even tell the difference there. Okay, so that is important, because that's how we're going to deal with real data. Let's look at real data. The real data is right here. I got it from this ourworldanddata.org/coronavirus. And that's not it. That's it. Okay. So this is some of the countries. China, you can see it does look like an exponential growth. Here's Iran. And I started them all from the same time. This is USA. We had very, very few, but now we're starting to increase. This one is Italy, and so forth. And right here, you see this big jump in the China data. I think it had to do with how they defined who was infected. So that just changed their numbers there. But we're cool. We're cool with that. Okay. But how do we find the growth rate from this? Let's go back over here. Okay. So if I have this function, and I divide both sides by n0, and then I take the natural log of both sides, I get this. So here I have the natural log of the number at any given time divided by the starting number. And you have to do this because you can't take the natural log of something with units, even days. And that's just going to be equal to AT. So now if I plot the natural log of the number of people divided by the number of start, And then versus t, it should be a straight line. This versus t should be linear, and the slope of that should be a. And that's exactly what I did right, no, here. So this is the log of the number ratio versus time. And you see here at the beginning of this, we get a pretty linear function for China. Most of them are pretty linear, Iran and so forth. There's at least some linear part to it that we can fit. But this one I have a slope of 0.394. So what I want to do is actually model this data. Okay. So let's go over here and start a new program. Okay, so again, we're going to have a graph. T graph equals graph. And I want to take, I'm going to use this. I'm going to write down here, A equals 0.394. And I want to plot the number of infected people in China and see if I can fit that. I want everything to work. Okay, so let's call this X title equals, it's going to be the same thing. Days, Y title, number, and then what did I have? The width of 500. Okay. Okay, so let's first plot the data. I actually got those first data points out. They're over here. So I've already pasted this as a list. So I just want to plot this. So let's do FC for China equals G dots. Color equals color.red. I need to want to plot those. Okay, so let's do this. Day equals 0. And let's say, here's how do you go through? You could manually go. I could do this. fc.plot 0, 2, 7, 8. fc.plot 1, 3, 10. Let's just run this now. And there you see my data points are there. So you could do it manually. Okay. So you don't have to do it this way. But there's another way I can traverse through that list. I can say for I in China, do the following. First, add 1 to the day. Next, plot f1.plot the day versus I. I is one of those numbers. I'm pointing to the screen. You can't see it. Okay, so now if I run this, error. F1, I call it FC. There you go. That's my data for China. Now I want to plot, make a function that matches that. Okay, so let's call this F2 equals G curve. Color equals color.blue. And now I need, let's say, N0 equals 1. T equals 1, dt equals 0.1, 0.5. And then let's say while t less than 9, I can do it either way, but let's just do it the exponential way. So let's say n equals n0 times the exponential a times t. I've already said what a is, and then add increase t plus dt, and then plot. Let's see what happens. Okay, and you see they don't match up because I made a classic mistake, right? And that here you see the number at day 1 was 278, and I had a number of 1. So if I put this at 278, I'm just repeating my mistakes I made it before. And now you see it's going to fit much better. It's still not perfect because I am at day 1. So really what I need to do is to look at the slope. This slope of that best fit line gives me this constant right here. But it also gives me the y-intercept. So if I use the y-intercept to calculate the number at time t equals 0, from the data, I get, let's comment out this. I get n0 equals the exponential of 5.1528. So that's the y-intercept from the fit. So if I take the exponential of that, I should get the starting number. Let's see how that fixes things. There you go. Check that out. That is that fits, right? So we get the data to fit. We get this model to fit the actual data. I mean, it's sad and depressing, but at least it works. Okay, one more thing. Where am I? Yeah, so how do I model this? So if you go to this great video by 3 brown, 1 blue, here's the link in here. I'll put it downstairs. I'll call it downstairs. We talk about one of the problems is how do we deal with this? N's not infinite. We can't have an infinite number of people, so eventually we can't keep infecting more people. Where did I put it? Right there. So this is one way to adjust it. What if I put this factor in here? What if there's some maximum number of people that can be infected? And so as N increases, this thing gets closer to N max. Once this gets to N max, then you have 1 minus 1 is 0, so no one gets infected, which makes sense. As N is very small, then this is just 1, right? Because you have 1 minus 0, so it should work there. So if you want to put this in an equation, again, I can go back to the delta N over delta T, and I can model it this way. So this is the same equation I had before, but now I have some maximum number of people. I have N is the same. This is the same thing. I just need to put this in my code. Let's see if this even works. Okay. So I'm going to go over to my previous trinket. The one I just saved. My trinkets. I know this is really long, but, you know, what else are you going to do? This one right here, and let's just copy it so we can start over. Okay, so now we want to take it. Let's run this, make sure it's doing what we want. Okay, so that's fine. So that's for exponential growth. So now let's say N max. I'm going to take out this other N. Let's take out this N2. Oh, let's leave it in there for now. Okay, so let's say N max is equal to, I'm just looking right here. We can pick a value for this. I'm going to pick, oh, well, here we had China was 0.394. And this was 0.394. And then in max, China's got a lot of people. Let's just say it's 300 million. So 300 E6. I don't even know if that's going to work. So here we're going to say A times 1 minus N divided by N max times ET. So I'll put that factor in there. That should be capital N max. Okay, I don't know what happened. Let's turn off F2. That's way too small, I guess. Let's put this at 1 billion. So let's say 2 billion. 1 million, 2 E9, right? 2 billion, no 1 billion. Huh. That's weird. N equals N plus A times dt times 1 minus this divided times dt. Why isn't that working? So it should be, if I have a small time interval, it should be the same, right? Let's do this for 5 days. Okay, they close. It's leveling off too soon. One. I guess I have to have this even bigger. No? What am I doing wrong? N equals N plus A times dt. Let's just put this at 1. Let's just put this at 1. See if that works. Oh, that's not even working. 0.394. Weird. Oh, n times a times n. I think I'm missing, that was it. I was missing an n. 1 minus n divided by n max times n times dt. Error. A is not a function. Times. Gosh. Okay. Now I think it's working. So now let's go to day 15. Let's just see. They're on top of each other. Let's make n max smaller. Let's say 1e8. 1e7. 10 million. Let's go even further. 45. There we go. Okay. Now it's starting to drop off. Now it's starting to work. Let's just say, let's go back to 10 to the 8th. Okay. Let's go 10 to the 7. And let's turn this off. Okay. There we go. Okay, so now you get exponential growth right down here and then leveling off. If we go back, this is a long video, right over here. This seems to level off at 80,000. Okay, so 80,000 would be the maximum number. Let's see if we put in 80,000, what it would look like. So n max is 80,000, 83. Yeah, and that levels off at day 38. Wow, that kind of worked. Okay, so I'll link this code down below too. Play around with these numbers, play with exponential growth, stay inside, social distancing, watch a lot of YouTube videos, and I hope to talk to you guys later.